Good morning. This is Math 1314, February 28th, the last day of February. A couple of announcements. WebAssign homework. You have section 5.1 is due today. I gave you an extra day or two to get 5.1 done. 5.2 and 5.3, I gave you an extra 2 days on that because originally it was scheduled for February the 4th. I'm sorry, March the 4th, and so I've pushed that back to March the 6th just to give you a couple of extra days on 5.2 and 5.3. 5.4, 5.5, and 5.6, notice, are due on the 18th of March because that's after spring break. And so you've got a decent amount of time to get those done. But please, please don't wait until March the 17th and March the 18th to do that, right? Get some of that work done ahead of time and try to take care of WebAssign so that you don't find yourself on March the 18th frantically trying to get that work done. All right, and then one other thing to announce here that I didn't leave room for, but the Exam 2 review will be posted. Let's see, I was actually looking at it some yet last night, so it'll be posted on probably around March the 7th. Right, so that's next week, and so the Exam 2 review will be going up pretty quickly. This should make some of you happy. I know Anne-Marie kind of was not nervous about this, but didn't like this about Exam 1 review, but most of the Exam 2 review are problems that I'm actually giving you on the review, not problems out of the textbook, but my own problems. And about 90% of the Exam 2 review is going to be my own problem. Maybe 95% of Exam 2 is going to be my own problems that I'm putting on the test, and then the answers will be on the review also. So it's going to be a lot less on Exam 2 review. It's going to be a lot less problems out of the textbook that I'm pulling to give you. So hopefully that will help some of you as far as preparing for Exam 2, and that that'll give you some good practice. There'll be plenty of problems there for you to practice, that's for sure. All right, so today we are going to continue talking about polynomial functions, and so we got a lot to do today. We're going to look at section 5.4 on dividing polynomials, and then all of the rest of this, for the most part, is section 5.5. There's a lot in section 5.5. We're coming out of section 5.2 and 5.3, and so I want to kind of give you, again, kind of an overview. I think it's important that you have an overview of what we're doing, and so you can kind of see the big picture and how this is all fitting together, because this is kind of like to me, it's all like a big puzzle when you're talking about polynomial functions and how this all fits together. So on section 5.1, we were looking at second degree polynomial functions, right? That's what section 5.1 was all about, was second degree polynomial functions. And remember, that's just, we don't usually call them second degree polynomial functions, do we? We usually call those just quadratic functions. And we know that those graphs are all parabolas. And there's this nice set of information that I'm going to be asking you to find for quadratic functions, right? I'm going to ask you to find the vertex for the parabola, and I'm going to ask you to complete the square to do that. There is a formula for calculating the vertex. I am not asking you to use the formula. I'm asking you to complete the square to find the vertex. On the exam, it'll say complete the square to find the vertex. I'm going to ask you to find the axis of symmetry, and then the x-intercepts and the y-intercepts. See, so for example, on the exam, going into the exam, you know for a fact that that's the information I'm going to ask you to find for quadratic functions, is I'm going to ask you to find those four things: vertex, axis of symmetry, x-intercepts, and y-intercepts. Remember, the x-intercept, you set y equal to 0. The y-intercept, you set x equals 0. But you know that that's what I'm going to ask you to find for polynomial functions. And then in section 5.2, we started looking at polynomial functions where the degree was higher than 2. So the degree is greater than 2. So 3, 4, 5 are typically the ones that we're going to be looking at. And in particular, in section 5.2, we learned how to write down the degree for a polynomial, whether it was factored or just in terms. We talked about the leading coefficient for a polynomial, in particular whether the leading coefficient was positive or negative. And then the end behavior. Right, so remember the end behavior, we talked about the idea whether it's rising to the right, falling to the right, rising to the left, falling to the left, like that. And so we looked at the how to take the degree and the leading coefficient, put those together to actually write down the end behavior. So we introduced that in section 5.2. And now in 5.3, we are starting to extend this list. And so we are starting to talk about the zeros for a polynomial function. And remember, there are 3 kinds of zeros, so that's something to start talking more and more about. There are rational zeros, and I've talked about this now twice in lecture, irrational zeros and imaginary zeros. And we're going to talk more about that in class today during lecture. And then we talked about x-intercepts and y-intercepts, right? The x-intercepts are still, come from the zeros. And if you have rational zeros, you get x-intercepts. If you have irrational zeros, you get x-intercepts. Imaginary zeros, no x-intercept there. Right, so the x-intercepts, you're just getting those from the zeros, and then the y-intercept, as always, you're just setting x equals 0. See, so notice I've established this list of things that I'm going to want you to find for polynomial functions. The degree, the leading coefficient, the end behavior, zeros for the function, the x-intercept, and the y-intercept. And where the hang-up is with polynomial functions is with zeros and finding the zeros for the function. That is the place that causes us quite a bit of issue as far as how to deal with finding those zeros, because that can be easy to do or it can be harder to do, and depending on the problem. And so this is what we've done with finding zeros so far, is if the polynomial is already factored, like so, let's see, let me back up here just a second. So already factored, we've talked about these. So when I say already factored, if a polynomial looks like this, f of x equals x plus 3 times 2x minus 3 times x squared plus 4, let's say. Right, that's a polynomial that's already factored. And so for finding the zeros for this function, this is actually not that bad to do, because you're setting y equal to 0. And because you have these factors like this, all you've got is a bunch of factors set equal multiplied to give 0. And so the only way that can be true is by setting each of these factors equal to 0, right? So if the polynomial is already factored, finding the zeros is easy, because all you've got to do is set the factors equal to 0, right? And so you get the zeros to be -3. On the first one, you just subtract 3. On the second one, you have 2 steps there, right? You have to add 3 and divide by 2. So you get 3 halves. And the last factor, x squared plus 4, x squared plus 4 is not factorable, remember, because it's the sum of squares, and the sum of squares does not factor like the difference of squares does. But you can solve this using the square root method by just subtracting 4, and you get plus or minus 2i. Right, so the zeros for this function are at -3, 3 halves, and plus or minus 2i. Don't forget that the number of zeros for a polynomial equals the degree of the polynomial. So in this case, this is a fourth degree polynomial. We should get 4 zeros, and that's what we found, are 4 zeros, right? So if the polynomial is already factored, finding the zeros is not that hard to do, right? So we talked about this in section 5.3. So you've got examples in the lecture from last time on Monday for polynomials that were already factored. And then we also looked at, excuse me, polynomials that are not already factored, but that are easily factorable. And when I say easily factorable, I'm just saying that using methods from intermediate algebra, you can factor the polynomial even though it's not in factored form. So like this problem, f of x equals x cubed minus 3x squared minus x plus 3 is not in factored form. So I can't just tell what the zeros are by looking at this polynomial, but I can factor this by grouping, right? And so since it factors by grouping, then I can factor it first, and then I can find the zeros from there, right? So this polynomial, the first two terms have a common factor of x squared, and I take that out, and I'm left with x minus 3. The second group has a common factor of -1, so you factor that out, and you have an x minus 3 there also. So that gives me a common factor of x minus 3. I take that out, and I'm left with x squared minus 1. And then x squared minus 1 factors x plus 1 times x minus 1, like that. See, so even though this polynomial was not factored, it was easily factorable. These problems are also in section 5.3. And again, you have examples of this kind of problem in your notes from last time. So now the zeros are easy, aren't they? From the factors, you get from x minus 3, you get that x has to be 3. From x plus 1, you get -1. And from x minus 1, you get +1. Right, so you get the zeros, and then those would be the x-intercepts, and then you kind of finish up the problem from there, right? So remember, right now we're just simply kind of giving you an overview of finding zeros here. And this was a third-degree polynomial. It made sense. We had 3 zeros here. All right, so in section 5.3, we looked at 2 kinds of polynomials. We looked at ones that were already factored, and we looked at ones that were easily factorable, right? Because finding the zeros in both of those cases is not that hard to do because you've got these nice factors and you can just set them equal to 0. The problem is most polynomials, or a lot of polynomials, don't fit into those 2 categories. They're not easily factored, and they're not in factored form already. So like, and this is section 5.5. So in section 5.5, for example, we have this, for this polynomial, we have f of x is 2x cubed minus 9x squared plus 13x minus 6. Right? That one is not in factored form, and it does not, there's 4 terms there, it does not factor by grouping. But still, this polynomial is factorable. There is a way to factor it. It's just not as easily factorable. So it's not in factored form. Right? So it's not in factored form. It's not easily factorable. Right? Grouping does not work here. And there's no GCF. And so the question is, how do you find the zeros for this kind of function, right? How do you find zeros for this kind of function? So how do we find the zeros here? Right, that's what we're talking about in sections 5.4 and 5.5, is how do we find the zeros? Now, what I want you to be noticing as we go through this is that, and we did mention this last time certainly, but what happens that a factor, like here in the first problem, x plus 3 is a factor and negative 3 is the 0. Right? In the second problem, x minus 3 is a factor and 3 is a 0. And so what do we have here is that factors and zeros go together. Right, that when you get a factor, a linear factor for a polynomial, you also get a 0, and when you get a 0, you get a linear factor. Right, so those always go hand in hand. So if we have f of x equals x minus 5 times x plus 6 times x minus 3, right, the zeros are going to be 5, negative 6, and 3. And so what do you have? That every time you get a linear factor, you get a 0. Every time you get a linear factor, you get a 0. Right? Factors and zeros go together. And you could do the other way also. Right? So you could, if I started with the zeros for a polynomial, so like let's say the zeros were at 8, negative 4, and 6, right, then we could write the polynomial from that. Because since x equals 8 is a 0, then that would mean that x minus 8 has to be a factor, right? So that the 0 of 8 gives you the factor x minus 8. Since negative 4 is a 0, x not x minus 4, right? But this would have to be x plus 4. That would be the only way to get a negative 4 there, right? Because you're setting the factor equal to 0. So it's got to be x plus 4 has got to be the factor. And then x minus 6 has to be a factor, right? 6 is a 0. X minus 6 has got to be a factor. Right, so you can actually build the polynomial from the zeros if you wanted to, because you know that zeros and factors, right, go hand in hand. Right, and I say factors, I'm talking about linear factors here, remember. So in fact, you can say it this way, that if x equals k is a 0, then what has to be a factor? What has to be x minus k is a factor. So if x equals k is a 0, right, x minus k is a factor. This idea is sometimes called the factor theorem. Right, factor theorem is telling you that zeros and factors go together. Right, when you have a 0 for a polynomial, you get a factor. That's a big deal for us with polynomial functions. That when you get a 0, you get a factor. And vice versa, right? That those things go together when you're talking about a polynomial. So what we want to do is concentrate on factors. If we can get a factor for a polynomial, then we know we've got the 0. So we're concentrating here on getting factors. And so the question here is, how do you know something's a factor or something else? So for example, let's do something really simple here. So we are going to concentrate on finding factors. Right, and then once we get a factor, then we can get a 0. All right, so how do we know 7 is a factor of 28? Something super, super simple. How do we know that 7 is a factor of 28? How could you prove it to somebody that 7 was a factor of 28?
Divide.
That is it. Anne-Marie, that is, it's almost like I paid you ahead of time to tell me that, because that is absolutely perfect. That's exactly what I'm talking about, is you divide. That is exactly what I wanted you to say. And that is exactly right, right? And so to prove that 7 is a factor of 28, like Anne-Marie said, we divide it. And the idea here is that when you divide, what's going to happen? We get a whole number. We don't have a remainder, right? There's no remainder here when we divide. And you're right, it's all about division. And so that's how we can tell, this is exactly how we can tell whether something is a factor of something when you've got polynomials, is that you can divide polynomials exactly the same way. And if you get 0 as a remainder, then you've got a factor for that polynomial. Right? So, like, for example, if we wanted to show that x minus 1 is a factor of 2x cubed minus 9x squared plus 13x minus 6. Right? So if we wanted to show that x minus 1 is a factor of that, then what we would do is we would actually divide this. We would actually take 2x cubed minus 9x squared plus 13x minus 6, and we would divide it by x minus 1 and show that 0 is the remainder when we do this. Now, this kind of division right here, actually, technically, this kind of division is what's called a long division problem, where you actually have to go through long division to divide this out. Now, long division is kind of a yucky process. It's kind of a messy process to go through. But the good thing is, so first of all, this is long division. And if you've taken intro algebra, intermediate algebra, you may have talked about long division, but it looks like this. Right, and then you have to kind of go through the division. Now, I'm not actually going to spend the time to go through the long division here, because what happens is if you have a polynomial divided by something in the form x minus k, a shortcut for long division exists. And this shortcut for long division is called synthetic division. Now, some of you, for those of you who are watching live right now, the three of you guys, and those of you who are going to watch this recorded later, some of you may have dealt with long division, and possibly some of you haven't. I'm going to assume you have not done long division or synthetic division before, and I'm going to show you how to do this kind of from scratch, okay? So synthetic division works for this one kind of long division, this one kind of division where you're taking a polynomial and dividing it by something in the form x minus k. The good news is that's the only kind of division we need to find zeros for polynomial functions. And so we're going to be able to do this with just using synthetic division. We're going to be able to work these kinds of problems using synthetic division only. And so this is the shortcut, okay? So I've got my problem here, 2x cubed minus 9x squared plus 13x minus 6, and I'm dividing by x minus 1. All right, so when I do that division, I find the k value, whatever the k value is, and remember, you're dividing by something in the form x minus k, and I put the k value down. I kind of put a little half box around it. And then I leave a row adjacent to the k open, and then I put a vertical bar kind of underneath it like that. And then what goes in alongside the k are the coefficients of the polynomial that you are dividing into. Just the coefficients. So you take the coefficients of that polynomial, and I write them here in order. So that'd be 2, -9, 13, and -6. Right, just the coefficients. And now, whatever this first number is right here, doesn't matter what it is, whatever it is, you always bring it down below the line. So I put the 2 down here. Whatever that number is, you bring it down below the line. And then what we're going to do is, and then I'm going to actually do this on the problem we're talking about. You take the k value and you multiply it by the 2. You multiply there. You write that number in the next column right there, and then you add. So this is multiply right here, and then this is add right here. And then what you do is you do that over and over again, where you have a number here, you multiply, and then you add again. And then you get another number right here. And then you multiply. It's always multiplying by the k value. And you put that number right here, and then you add. And you bring a number down this way. And it's always going to be multiply, add, and it's always multiplied by that k value. So in my problem right here, and actually I'm going to start with a different number to divide by. You'll see why in a minute. But so if I divide this by x minus 3, instead of x minus 1, I divide by x minus 3. So the k value here is 3, right? Because remember, it's x minus k, right? This is x minus k right here. And so you have to figure out whatever the k value is. And since it's x minus k, the k value would be positive 3. You write down the coefficients. And then you start going through this process. You bring the 2 down, like I said. You take 3 times 2, which is 6, and you add it in the next column, or you put it in the next column, and then you add. So that'd be negative 3. And then 3 times negative 3, you go through the same process again, is negative 9, right? So remember, you're always multiplying this way by the k value. You write in the next column. You add, then you multiply again by 3. You write in the next column, you add, and you keep on going like that. Right? So that would be, that would be 4 right there. 3 times 4 is 12. You write that in the next column, and you finally add, and you get 6 like that. All right, when you've gone through the division, completed the little chart that you've created here, the last number right here, this 6 in this case, is the remainder. And then the quotient is represented by these coefficients right here. And the quotient is always degree 1 less than the original polynomial. The degree is 1 less than the original. So the degree of the polynomial, that's the quotient, would be a degree 2, since we started with a 3rd degree polynomial. So this would be 2x squared minus 3x plus 4. But then because there's a remainder, there's a fraction stuck on at the end. And the fraction is always the remainder over the divisor. So it'd be 6 over x minus 3. And you stick that fraction on at the end like that. And if you think about it, that's exactly what you do when you use division with just whole numbers, like 29 divided by 7. Right? 29 divided by 7 is 4. 7 goes into 29 4 times, but there's a remainder, and the remainder is 1. And so what do? You write the 1 over the 7. Right? It's always the remainder in the numerator and the divisor in the denominator. So we do exactly the same thing with polynomials. We just stick the remainder over the divisor on at the end as a fraction. Right, and so we've gone through our first synthetic division problem. We've actually divided. And so now notice, because we got a remainder here, what do we know? Because there is a remainder on this last division, we know that x minus 3 is not a factor of the original polynomial, right? X minus 3 is not a factor. And the reason why is because the remainder was equal to 6. And the remainder should be 0 if it is a factor, right? So now let's go on to some more examples of synthetic division and this kind of thing. So let's go we're still using our same polynomial, 2x cubed minus 9x squared plus 13x minus 6. But now it's divided by x minus 1, which was the original one that I was going to do. So the k value here is 1. And you divide it into these coefficients. Right, 2, negative 9, 13, negative 6. Leave a space underneath, put that horizontal line. Bring the 2 down. So then we start multiply, add, right? So 1 times 2 is 2. Write it in the next column. Add, get negative 7. Multiply again. 1 times negative 7 is negative 7. Write it in the next column. Add, you get 6. 1 times 6 is 6. Write it in the next column. And notice in this case, you add and you do get 0. Aha. So the remainder is 0 here. And so that means that x minus 1 is a factor of the original polynomial. And the great news here is not only is it a factor, but we also get the other factor, right? The other factor is the quotient, is the answer to the division problem, right? And so we actually have partially factored this polynomial, that x minus 1 is a factor. If the polynomial was 2x cubed minus 9x squared plus 13x minus 6, then we have partially factored it. X minus 1 is a factor, and the other factor would be 2x squared minus 7x plus 6, like that. And so we actually have it partially factored. And we've got a factor that's a quadratic. Actually, this is even better, because that is now easily factorable as an intermediate algebra student. You can factor 2x squared minus 7x plus 6. You have a 2x and an x there, and it factors 2x minus 3, x minus 2. And so notice this is a problem where if we divided, we could show using division that x minus 1 was a factor. We could actually now find the zeros for this function, right? If we have f of x is 2x cubed minus 9x squared plus 13x minus 6, what have we done here? Well, first of all, let's write down the degree. Let's do all the things that you would do as on a test question. The degree of this polynomial is 3. The leading coefficient is a positive 2, so it's positive. The end behavior for this function, I just usually write the word end kind of for short, but remember we're talking about end behavior. And the end behavior for this function, because it's an odd degree polynomial, leading coefficient is positive. Remember, we can draw it out. Odd degree means that the end behavior looks like the cube function. So it means it's falling to the left and rising to the right. Or you could say that as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity, like that. So we get those things, but now in addition, if we want to find the zeros for this function, right? So what do? We start with the function itself. F of x equals 2x cubed minus 9x squared plus 13x minus 6. But using synthetic division, we were able to show that x minus 1 was a factor. Right? And this was using synthetic division and the factor theorem. And then we were able to factor the 2x squared minus 7x plus 6 and get 2x minus 3 times x minus 2, like that. And so using that synthetic division, now how do we find x minus 1? Well, I just told you to divide by x minus 1, right? So that's still a question, is how do we know to start with x minus 1? But once we've got that far, then we could write down the zeros, that the zeros are x equals 1, x equals 3/2, and x equals 2. And remember, the zeros and the factors go together here. All right, so this kind of starts getting us headed in the right direction. This is a good thing here, that we can find zeros for a function using synthetic division. And we can actually prove something's a factor using synthetic division. So this is a good start. All right, so now let's talk about this polynomial right here. Next, let's talk about the polynomial f of x equals 4x cubed minus 7x plus 3. All right, so let's first of all, let's look at this question. Is x minus 4 a factor? That's the question. Is x minus 4 a factor for this polynomial? I'm going to say of f of x. Is x minus 4 a factor of f of x, that polynomial at the top? So now we know how to decide to do that, right? We look at this division problem, 4x cubed minus 7x plus 3 divided by x minus 4. And so there's a couple things that I want to talk about here. Definitely, a big thing here that's an easy mistake is you have to find the k value, right? So x minus k is x minus 4, so the k value is 4, so we're dividing by 4. And then we write down the coefficients of 4x cubed minus 7x plus 3. Now you got to be careful here. You have to write down all the coefficients. And notice there is a x squared term. X squared term is missing in this polynomial, right? There is no x squared term there. So when you write down the coefficients, you've got to write a 4, and then you have to put a placeholder for the x squared that's missing, and then a negative 7, and then a 3. So any term that is missing must have a placeholder when you write out the coefficients here. It's really easy to forget to do that, and then you're going to then you don't have the right polynomial anymore, and you're going to miss the problem. All right, so we bring down a 4. The first number, we multiply, you get 16. You add, you get 60. You get 16. And then 4 times 16 is 64. You add, you get 57. And then 4 times 57 is 228. You add there and you get 231. That is our remainder right there, is 231. And so what's the answer to the question? Is x minus 4 a factor? And the answer here is definitely no, right? Because you get this remainder of 231. Now, we're going to continue to look at this problem, but before we do anything else here, I do want to point out that if you looked at f of 4 in the original function, and why did I use 4? It's because 4 was the number I happened to be dividing by synthetically. So if you look at f of 4, that's 4 times 4 cubed minus 7 times 4 plus 3. So this is 4 times 64 minus 28 plus 3. So this is 256 minus 28 plus 3. And notice you get 231. You get the same thing as the remainder. That's actually something called the remainder theorem. And the remainder theorem states that if you divide synthetically by, let's say, k, like that, and you get a remainder down here of r, that remainder r is always the polynomial evaluated at k. So if the polynomial is p, that would be equal to p of k. This is the coefficients of p of x right here. In other words, the remainder is always what you would get if you substituted that value into the function. It's called the remainder theorem, and it's actually a somewhat more efficient way of calculating function values for polynomials. And rather than plugging numbers in, you can actually use synthetic division. All right, now let's continue to talk about this polynomial. So we've answered the question, is x minus 4 a factor of this function? No, it's not. So the next one is x plus 6 a factor of f of x? All right, so now, so this is the polynomial division we're looking at, is 4x cubed minus 7x plus 3 divided by x plus 6. And so x minus k, in this case, you've got to be careful. X minus k has got to be x plus 6, so k has to be negative 6 here. Most students just simply remember that is that the k value is always the opposite sign of what you see in the binomial. So we're going to divide by negative 6 here. Don't forget the 0 as a placeholder when you do the division. And so you bring down the 4. Negative 6 times 4 is negative 24. You add, you get negative 24. Negative 6 times negative 24 is positive 144. The numbers can definitely get big sometimes when you do synthetic division. 144 and negative 7 add to give you 137. And then negative 6 times 137, I'm going to cheat here and get my calculator out just to make sure I don't screw that up. 6 times 137 is 822, and this would be negative. And then you add and you get negative 819. Negative 819 is the remainder. And so the answer is x plus 6 a factor of f of x. The answer definitely, again, is no. But using the remainder theorem, we did get some information here that the remainder theorem tells us that f of negative 6 is equal to negative 819. In other words, if you look at the graph of this function, it goes through the point negative 6, negative 819. So the remainder theorem does give you that piece of information. All right. Let's look. We're going to continue looking at this polynomial. So we've checked two factors, x minus 4 and x plus 6. Now, where did x minus 4 and x plus 6 come from? I picked those completely out of thin air. I just made those up, made them out of thin air. And so let's see if this is a factor. Why not? So we're continuing to look at 4x cubed minus 7x plus 3. And so another question is x minus 1 a factor? Right? So we know, based on what we've talked about, that we're going to divide synthetically by 1. And so we write down the coefficients of our polynomial. 4, don't forget that there's no x squared, so we write a placeholder and then negative 7 and then 3. All right, so we bring down the 4, and then we go through our little multiply and add routine, go through the synthetic division. So 1 times 4 is 4. Write it in the next column. You add, you get 4. 1 times 4 is 4. Add, and you get negative 3. 1 times negative 3 is negative 3. You add, and you do get 0, don't you? Right? And so is x minus 1 a factor? And the answer here is, because the remainder is 0, the answer is yes, it is a factor. Right? Because the remainder is 0. not only is it a factor, but we get the factorization because we have the other factor. Remember, the other factor is always got coefficients that are this bottom row. And the degree of that other factor is always one less than the original polynomial. So the original polynomial was a third degree polynomial. So this new factor has to be a second degree polynomial. And it would be 4x squared plus 4x minus 3. Not only do we get that other factor, but now we can just use methods from intermediate algebra, and we can go ahead and factor that polynomial as well. This is a 2x and a 2x here. And let's see, we would have 2x plus 3, 2x minus 1, like that, and that's how it's factorable. And so we get, because we can factor it like that, notice we get all the zeros for the polynomial. Right, the zeros are going to be, because x minus 1 is a factor, we get x equals 1 is a 0. Because 2x plus 3 is a factor, remember, you're setting that factor equal to 0 and solving, you get negative 3 halves. And then because 2x minus 1 is a factor, we get 1 half is a 0. Remember, the zeros and the factors always go together, like that.
I have a question.
Absolutely.
On the problem when we make the x 1 less, wouldn't it be, let's see, where am I? It would be x squared, 4x, I wrote it down. No, I didn't. It would be 4x squared, oh, I'm on the wrong page, that's why. 4x squared minus 4. Wouldn't we drop the x next to the 7x, negative 7x?
I'm kind of confused. Okay, Charlotte, go ahead. Try it again, Charlotte.
Problem. Sorry, the original problem is 4x cubed minus 7x plus 3.
Correct.
So wouldn't, after you do all the division, the synthetic division, isn't the x value 1 less than the original problem?
The degree of the new polynomial, of the new factor, is 1 less than the original one. All right, so
this negative 7x would make 4.
No, it has nothing to do with the negative 7x. It's what's the degree of the original polynomial? The degree of the original polynomial is third degree, right?
Okay, so just the original, okay.
So the degree of this polynomial is 3. So that means the other factor here has to have a degree of 2. And so what that tells you is where to start the terms with, what degree you start the terms with. So this is the x squared term right here. Then this would have to be the x term right here. And then this would have to be the constant term right here.
Okay.
Right. So that just gives you the place to start. What power of x do you start with when you write down the other factor here?
Got it. Thank you.
Okay, does that make sense?
Yes.
Okay. All right. So and believe me, we're gonna have lots of practice with that as we go through this. So all right. So let's see. I'm trying to find the next problem I want to work here. So now, all right, so let's go on to another problem here. Let's start off with this polynomial. F of x equals 3x cubed plus 9x squared plus x plus 3. And so what I want to do here is I want to find all the zeros given that negative 3 is a 0. That x equals negative 3 is a 0. All right, so now when I say find all the zeros, what do we know about this polynomial? We know it's a degree 3 polynomial. And so that means it has to have 3 zeros. Right? Remember, the degree of the polynomial and the number of zeros is always the same. And I've got one of them. I've got -3. I've given you that -3 is a 0. And so then the question is, how do you find the other 2 zeros, right? So, so that's really the question. How do we find the other 2 zeros? Well, so if 3 is a 0, right, if x equals 3 is a 0, then what that tells you is that x minus 3 is a factor. Remember, those two things go hand in hand. That a 0 and a factor always go together. So what should happen here? Then that means that when I divide synthetically by 3, I better get 0 as a remainder. And if I get 0 as a remainder, then I get the other factor, right? The other factor is sitting down here below the line. And this, Charlotte, is what you and I were talking about a minute ago will come into play as to how to write out that other factor here. All right, so that's how you attack this problem. Go ahead and divide synthetically by 3. I'm sorry, divide synthetically by -3, because you know that, oh, wait a minute. A little bit, I miswrote here, right? Find all zeros given that x equals -3 is a 0. And so this should be x equals -3 right in here. I need to erase some things here. So x equals -3 is a 0. And so that means that x plus 3 is the factor. And I was dividing synthetically by -3 right there. Okay, so now I've got that straight. So let's see what happens here if I do the synthetic division. So I write out the coefficients, 3, 9, 1, and 3. That's from the original polynomial, remember. And then I do the synthetic division. So I bring the 3 down below the line. -3 times 3 is -9. I add and I get 0. -3 times 0 is 0. So I add, I put that in the next column, which is a 0. That's okay. That can happen. Add and you get 1. And -3 times 1 is -3. And add and I do get 0. Right? Which is what we're supposed to get, right? We're supposed to get 0 as a remainder. So this proves right here that x plus 3 is a factor. But not only does it prove that x plus 3 is a factor, it also proves that the factorization looks like this. X plus 3 times, and the other factor is sitting below the line. And so Charlotte, you and I were just talking about this on the last problem. So the original polynomial is a 3rd degree polynomial. So the new one would have to be a 2nd degree. And this would be the coefficient of the x squared term. 0 would be the coefficient of the x term, and then the constant would be the 1. And so notice this polynomial ends up being 3x squared. The coefficient of the x is a 0, so that means there is no x term, and it's just 3x squared plus 1. There's the other factor. Right? And so we've got the factorization for that original polynomial. It's x plus 3 times 3x squared plus 1. And so where do the other 2 zeros come from? The other 2 zeros are in that factor right there. Right? That's where the other 2 zeros are sitting, is in that factor. Now, what would be nice is if that was actually factorable. Unfortunately, it's not factorable. So to find the other 2 zeros, we take that second factor, set it equal to 0, and we would actually, in this case, could solve that using the square root method. So you'd subtract 1 and divide by 3. Yuck, you get -1/3. And then you take the square root and you get plus or minus the square root of -1/3, which is plus or minus I times the 1 over the square root of 3. Right? Because it's I because it's the square root of a negative number. So you get an imaginary solution there, or imaginary value. And then if you wanted to rationalize this, remember WebAssign will always rationalize. So if you rationalize by multiplying by the square root of 3 over the square root of 3, you get the square root of 3 over 3. So those are the other two zeros. So the zeros for this function are negative 3. That was the one we were given. And plus or minus I times the square root of 3 over 3. The x-intercepts, remember the zeros and the x-intercepts kind of go together. Negative 3 is a 0, so negative 3, 0 would be an x-intercept. But the other two zeros are imaginary, so I don't get any other x-intercepts, right? There's no x-intercepts from imaginary zeros. Right, so don't forget that you don't have any x-intercepts from those imaginary zeros. So there's only one x-intercept in this function, that's negative 3, 0. All right, so now this is starting to kind of, some things are kind of starting to emerge here as far as how to find these zeros. The problem here is I gave you a 0 at the beginning of the problem. I gave you that negative 3 was a 0. So the question is, what if you aren't given a 0 for the polynomial? Then how do you find all the zeros, right? So like, let's look at this problem right here. You have f of x equals 3x cubed minus 11, minus x squared minus 11x minus 6. And the instructions here were just find all the zeros. Find all zeros. Notice I'm not giving you a 0 at all. I'm just saying find all of them. So the question is, where do you start? You know, on this last problem, I gave you that negative 3 was a 0. Right? We were given that negative 3 was a 0. And so that gave us a place to start the division. Right? That when negative 3 was a 0, that we would start dividing by negative 3. And then that would give us 0 as a remainder, and that would allow us to find the other factor. So the question is, what happens if you're not given that? And so this is the last theorem we want to talk about today. And so what we're going to do is talk about, there's still some theorems we haven't discussed yet, but this is called the rational zero theorem. We're going to use actually the rational zero theorem in conjunction with the graph of the function. We're going to actually use our graphing calculator to graph it and use that in combination with the rational zero theorem to figure out where we would try to start doing the synthetic division. So the rational zero theorem goes like this, that all rational zeros for a polynomial function are always in the form a factor of the constant divided by a factor of the leading coefficient. Always in that form. So what you do here with the rational zero theorem is you write down all the numbers that look like that. You write down all numbers in this form. That makes like a list of numbers, and all rational zeros are in this list. Right? All rational zeros are in this list. So in our particular problem here, what is the constant term? Well, the constant term, go back up to the original polynomial, the constant is negative 6. And the leading coefficient is 3. So what are the factors of -6? And by the way, it doesn't really matter that it's -6, and you'll see why in a second. But the factors of 6 are 1, 2, 3, and 6. But it could be +1, +2, +3, +6, or -1, -2, -3, -6. So it's plus or minus all those factors, and it's always going to be plus or minus all those factors like this. And the factors of 3, a shorter list, plus or minus 1 and 3. So the list, and this is the list of possible rational zeros. Notice these are just possible ones. Doesn't mean just because they're in this list doesn't mean they are rational zeros. It just means that that in this list, all the rational zeros are in this list somewhere. All you do is you write down all the numbers that are in the form of a factor of the constant divided by a factor of the leading coefficient. So all you do here is you take all the factors of the constant and you put them over the first factor of the leading coefficient. Then you take them all and you put them over the second one. And if there's a third one, you take them all and put them over the third one. And you do all these divisions. Now that sounds complicated, but it's really not a big deal because you take 1, 2, and 3, 1, 2, 3, and 6 and divide them by 1, and you get 1, 2, 3, and 6. You take 1, 2, 3, and 6 and divide it by 3, and you get 1/3, 2/3. Now the next one is 3/3, but 3/3 is 1, so it's already in the list, so I don't need to write it. And then the next one is 6/3, which is 2, which is already in the list. I don't need to write it. So these are the possible rational zeros. And then notice you put a plus or minus in front because it could be the negative of any of those also. And so for this particular function, 3x cubed minus x squared minus 11x minus 6, if it has any rational zeros, it's guaranteed to be one of those numbers in that list. And there's a total of 12 numbers in that list because of the plus or minus there. There's 12 numbers in the list. Now, we're not going to have to go through and divide synthetically by all 12 of those. Don't freak out. What we're going to do here is we're going to then use our graph of that function. So we would get our graphing calculator out. And from that graph, we would figure out which numbers to divide by. So in my case, I would take the my app here, and you would use either an app or on your phone or your graphing calculator. On a test, you'd use your graphing calculator to graph the function, which is what I'm doing right now, right? So there's 3x cubed minus x squared minus 11x minus 6. And then I look at the graph of that function. Whoa. And so the graph of that function on if you were going to graph this on a graphing calculator, you'd get something that sort of vaguely looks like this one in the decimal viewing window. It would probably look about like that right there. And so I would hope that I could use this graph to figure out what number to divide by synthetically. All right, so what I'm going to do is I'm going to save that as a picture, and then I'm going to bring it back here, and then I'm going to go to the next page, and I'm going to paste that picture in here. Make it a little bit smaller so don't have to take up quite as much room on the page here. All right, so now remember that the function is f of x equals 3x cubed minus x squared minus 11x minus 6. And the list of possible rational zeros from the last page, and this was using the rational zero theorem, was plus or minus 1, 2, 3, 6, and then we had 1/3 and 2/3. If there are any rational zeros, they have to be in that list, right? If they're not, if I have a 0 and they're not in that list, then they have to be irrational. Now, if you notice in this problem, there are three, in the graph, there are 3 x-intercepts. And those x-intercepts represent where the zeros are going to be, right? And so those are the x-intercepts. Those are also the zeros for this function. And so notice there's 3 x-intercepts. And so there's going to be, those are the 3 zeros. And so you're trying to match those up with your list to see if any of those match up with the list right here. So if you start off way over here on the far right, that number is -1 point something. It's a little bit smaller than -1, and there's no number in the list that fits that, that particular number. No number in the list fits that. So that means that that one's an irrational 0, quite likely. It's a 0, but it's an irrational one. Notice this number right here is 2 point something. There's no number in the list that fits that one. So probably irrational. Now this one, there may be a number that fits that one right there though. And because that one's not quite -1, and so -2/3 could fit this one. And so that tells us to divide synthetically by -2/3. Divide synthetically by x equals -2/3. And unfortunately, the first example I picked was a fraction. You know, they're not always going to be fractions. So the arithmetic's not going to be as bad as you think here. So I'm dividing by -2/3. That's okay to do. And I write down the coefficients. So it's 3, -1, -11, and -6. And so you bring down the 3. -2/3 times 3. The 3's divide out, luckily, and so that just gives you -2. You add, you get -3. -2/3 times -3, again, the 3's divide out, and this would be +2. -11 and 2 is -9. -2/3 times -9 is 18/3, which, sure enough, is 6. And I do get 0 as a remainder. -2/3 is a 0. Right? So x equals -2/3 is a 0. Not only is it a 0, but I get the other factor, right? You've got the first factor is, remember, it's always x minus the 0. So this would be x minus x minus -2/3, which would be x plus 2/3. It looks funny, but don't worry about the fact that it's a fraction. That's okay. And then this would be 3x squared minus 3x minus 9 is the other factor. And that comes from the bottom row right there. Don't forget that this bottom row are the coefficients of the other factor. Right, so that's where I get the 3x squared minus 3x minus 9. Now there is a common factor there of 3, so you can take the 3 out. I'm going to put that in the very front, and that would leave me with x squared minus x minus 3, like that. Now, unfortunately, the other 2 zeros are from that last factor. And so when I say unfortunately, because in this case, you have to use the quadratic formula to find the other 2 zeros. So I picked a problem, you know, to kind of start all this process with that maybe is not the easiest problem to go through because of a lot of these little things going on. So you get -1, the opposite of -1, right? You have negative b plus or minus the square root of -1 squared minus 4 times a times c, all divided by 2 times a. So you get 1 plus or minus the square root of 1 plus 12 over 2. And so you get 1 plus or minus the square root of 13 over 2. and those are the other two zeros. And those are actually the points on the graph up there, that this one is 1 plus the square root of 13 over 2, and this one over here is 1 minus the square root of 13 over 2. That those are the other two zeros there. And so the zeros for this function are if we're just going to list them, it would be negative 2/3 and 1 plus or minus the square root of 13 over 2. Like I said, I know it turned out to be kind of a messy problem there, but they're not all going to be quite that messy. Now I know that some of you who are with me live, maybe you have places to go. I don't know if you do or not, but what I'm going to do is usually I would shut down right now, but I really want to work one more example. So Anne-Marie, Ashante, Charlotte, if you stay with me, great. If you've got to go, that's fine. I understand that. But I am going to try to work one more example here, an example that's maybe a little bit nicer as far as the arithmetic goes, so you don't get a lot of the other stuff to cloud the issues here. So I'm going to work one more. You're going to find that the arithmetic on this one's going to be much easier than the last one. At least I'm hoping it is. So here's our polynomial as f of x equals x to the 4th plus 2x cubed minus 9x squared minus 2x plus 8. So if we started this one from the beginning, the degree of this function is 4. And the leading coefficient is a positive 1. And then the end behavior of the function, because it's an even degree function with a positive leading coefficient, this looks like the square function, and so the square function would be rising to the left and rising to the right, like that. So in other words, as x goes to negative infinity, y goes to positive infinity. In other words, y is rising as you go off to the left, and as you go off to the right, y is rising that way also. All right. So now with the zeros, we need to write the possible rational zeros based on what we just did on the last problem. The possible rational zeros are from the rational zero theorem. And so you look at the constant term, which is 8, and the leading coefficient, which is just positive 1 in this case, which makes it really easy. So all you're doing is looking at factors of 8, 1, 2, 4, and 8, divided by factors of 1, which is just 1. And so our possible rational zeros, all you do is you take all the factors of 8 and divide them by 1, and that's it, you're done. And so this is just plus or minus, don't forget the plus or minus, 1, 2, 4, and 8. All the possible rational zeros are in that list right there. Now, you don't just start dividing like crazy here synthetically to check those. Instead, you look at the graph next. So this is where we would bring into play the graph of the function automatically. So in this case, this is x to the 4th. So this is x raised to the 4th power plus 2x cubed, 2x raised to the 3rd power, minus 9x squared, minus 2x plus 8. So minus 2x plus 8. And then I look back at the function that I've entered to make sure that's actually the function I wanted to enter, which it is. And so I graph this one. And on my graphing calculator, if you graph this on a TI-83 or an 84 in the decimal viewing window, you'd get a picture very much like what I just have right here. It would look a lot like this one. So I put this in my photo library, and I'm going to go ahead and bring out the picture here. The very last one here. So that's this graph right here, but I'm going to go ahead and make this smaller. Fit it in right in here. All right, and so I've got 4 zeros for this function. That's what I'm trying to find here. And notice if you look at the graph, what you're focusing on in the graph are the x-intercepts and where the graph crosses the x-axis. And notice these look really like nice values here, and they all are numbers in my list. The very first, the one on the far right, or I'm sorry, the far left was x equals -4. That's a number in my list. This one is x equals -1. That's a number in the list. This one's x equals 1, a number in the list. And then finally x equals 2. That's a number in the list. So all I'm going to do here is I'm going to actually prove that these are actually zeros. So I take one of the numbers, and it doesn't matter which one. So I'm going to take 2, and I'm going to divide it synthetically to prove that these are zeros. So I bring down the 1, and 2 times 1 is 2. I get 4. 2 times 4 is 8. Add, I get -1. 2 times -1 is -2. I add, I get -4. 2 times -4 is -8. Add, I get 0. Okay, so we've proved that 2 is a 0. Not only have we done that, but we have also factored the polynomial, right? The factorization is x minus 2. And now be careful. The second polynomial, the second factor, is from the bottom row, and its degree is always 1 less than the original. So this should be an x cubed here. And then plus 4x squared minus x minus 4, like that. All right, then from my list, I pick another number from the list. So like 1, for example. But when I divide on that second 0, because I have another factor to find here, you divide into the new polynomial, not into the original one, but the new polynomial. So the new factor goes in right here. Don't use the original right there. Use the new factor. And then you go through the synthetic division. And notice you get, let's see, so I did something wrong there. So what did I do wrong? Because I'm not getting 0. Oh, I just miscopied. This should be a -4 here at the end. That's better. So 1 times 1 is 1. Add, I get 5. 1 times 5 is 5. Add, you get 4. 1 times 4 is 4. Add, you get 0. And so that is now my new factorization, is I've just proved that x minus 1 was a factor. So now I have x minus 2 times x minus 1 times my new factor, and my new factor is now x squared plus 5x plus 4. That one is a quadratic, and that actually is factorable. I don't need to use the quadratic formula or anything like that. That factor is x plus 4 times x plus 1. And now I've got all the zeros represented by factors. There's 2, there's 1, there's -4, and there's -1 from those factors. And those all agree with the x-intercepts on my graph. The important thing here at the end on this problem is when you get a new factor on your first synthetic division, that new factor has to be carried over into the next synthetic division, right? You have to do that. You can't use the original one because then you wouldn't be able to factor the original polynomial at all. Okay, so that was definitely an example I wanted to work through to try to start bringing some of this stuff together in some kind of a cohesive way. Now in this problem, I wouldn't be finished yet. I've got the possible rational zeros, and then I'd finish this. I kind of use some space with the graph, but I would finish this by writing down the zeros for the function, right? And the zeros for the function were just from the graph, right? So that's -4, -1, 1, and 2. And then I'd write the x-intercepts down, -4, 0, -1, 0, 1, 0, and 2, 0. And then finally, the y-intercept is super easy to find. You just set x equals 0 in the original function. And so when I set x equals 0 in the original function, right, so set x equals 0 there for the y-intercepts, you get 8. So you get a y-intercept of 0, 8. So the last part finishes up pretty quickly. All right, so I definitely wanted to kind of get that that part straightened out for you. If you wanted textbook practice here, and I know it can seem overwhelming at first on this, but believe it or not, students almost always get the hang of this and end up doing a pretty good job with this kind of stuff. Okay, so you'll be surprised that this will start making sense the more of these you work. So this is page 412, problems 7 through 39 odd. Those are the ones definitely that I would want you to look at there. All right. So thank you for you three for hanging on with me for this extra little bit of time here. Do you guys have anything that you need to ask about before we shut it down?
I'm good.
I'm good. I'm good.
All right, ladies, then you guys have a great day.